looking at A-PHY transmitter and receiver compliance testing. And we're very fortunate today to have Ramesh, who's the principal engineer at Tektronix, but more importantly for today is a key member of the MIPI test working group. And Ramesh is going to take us through the next part of the workshop. So over to you, Ramesh.
Thanks, Ian. So good morning, good afternoon, good evening, everyone. And today, I'm going to discuss about the transmitter and receiver compliance testing of an A-PHY interface. Before we get into this compliance testing, so let me go to the next slide. So let us take a look at the complexity of in-vehicle network test challenges and solutions. If you look at that in-vehicle network, it looks like this. So the electronic content in automotive is increasing at a rapid rate to cater the control, driving assistance, connectivity, and safety. In automotive, the primary vehicle uses more than 80 ECUs, which implements hundreds of distributed functions. In order to integrate all these functions and their communication relationship, a common link is used as a backbone. So if you look at that, wiring in automotive, that is the third largest contributor to the overall weight of the car and second largest contributor of overall bill of materials. Having this kind of the backbone link reduces the cabling effort, enables to reuse of component for different function, and allow us to download the software without having the dedicated flash. So the network should be more reliable for data transfer in automotive harsh environment and should be more stable with high EMI/EMC surroundings operations. It should also be a low cost, low in weight, and low in power. So in order to ensure the ruggedness of the network, the tests are being carried out at both semiconductor level as well as at the system level. So if you look at that, the data rate needs for the automotive network is increasing at alarming rate. If you look at it, the present electric and electronic architecture that consists of the many communication technologies. There are CAN, CAN-FT, LIN, FlexRay, Ethernet, and all are interconnected as central gateway shown here. The communication domain is introduced to group the similar core functions together and to divide the complexity of the overall system into a smaller manageable parts. The typical domains are powertrain, body and chassis, and infotainment, and advanced driver assistance. So the purpose of the objective of the advanced driver assistance that is ADAS is to prevent and reduce the number of accidents. As the level of the assistance increase from 1 to 2 or 2 to 3 means the driver assistance to the partial automation, the backbone network speeds are required to be increased from 100 Mbps to 1 gigabits. So if you look at it, if we go for then self-driving system, so we may need the backbone network up to a rate of 25 gigabits per second. So all of us know about the automotive Ethernet. It started with BRR under base T1, 1000 base T1, and now NG base T1. And now we have an A-PHY interface as well. The A-PHY interface can go up to 16 gigabits data rate. The need for higher data rate and reliable interface is must for the backbone or a sensor interface to meet these requirements. Now, let's take a look at the type of testing involved in IVN. So any network interface has got the physical layer we call is a physical media attachment unit. So in case of an automotive Ethernet, it is electrical in nature, and we need to perform the 5-layer testing. The messages are packed, and then we can test the message at protocol layer. The channel test is for testing the cable and used for testing the interconnect in network. The 5 receivers are tested to ensure the necessary BER is met with EMI interference. As Raj said in the previous presentation, we have to add more noise while testing the receiver. So when we put the network into a system, we also need to perform the interoperability test. The diagnosis test is common, and it is at the system level testing to ensure all the sensors are working fine. So when you look at the testing phase is started at for any time is started at as low as a component level, and then for a data for the trans receiver and at the trans receiver level. And then once these components have been put in the form of an ECU, then the ECU level test has been carried out. If you look at the production stage, the acid tests are being done at both at chip level as well as the system level and at wiring harness level. Now let's take a look at the A-PHY test. So before we get into the A-PHY test, let's try to understand that interface here. The A-PHY, so both Ido and Raj talked about the type of interface. A-PHY is a serial data interface with unidirectional high-speed data in one direction and low-speed data in the other direction. So the data rate is flexible and it is based on 5 types of gears, that is gear 1 to gear 5, and it can cater the data rate from 2 gigabits all the way up to 16 gigabits. It operates on duplex with the unidirectional high-speed data and bidirectional lower data rate used for command and control data streams. It also supports optionally the power supply so that the remote device can be powered with the A-PHY link itself. A-PHY also supports types of a cabling called the shielded twisted pair cable or shielded parallel pair cable, and it can support up to a length of 15 meters. A-PHY, with the flexibility of a data speed and the type of cabling, we can achieve high throughput data of sensors like camera and LiDAR. With the power being supported on the cable, the same A-PHY interface can be used for powering up the remote devices as well. If you look at that, A-PHY TX and RX testing. So as Raj said previously, there are 2 types of signalings that are called the profile 1 and profile 2. So we have 2 different types of the signaling. So the profile 1 is NRZ based signaling, and it is available to support from 2 gigabits, 4 gigabits, and optionally up to 8 gigabits. Whereas the Gear 3, Gear 4, and Gear 5 operates on PAM based signaling with PAM4, PAM8, and PAM16, so that the signal bandwidth needs are maintained at maximum of 4 gigahertz of the cable bandwidth. With profile 1 is intended for lower downlink speed and meet strong EMC requirements. The channel attributes enables the low-cost implementation. Apart from the automotive application, this interface can also be used for high-speed data transfer for other applications as well. It has unidirectional high-speed data stream and support bidirectional low-throughput command and control data stream on the same wire. So the downlink data speed can go up to 16 gigabits per second. The uplink is limited to 100 megabits per second. Both downlink and uplink can operate the profile as P1 or P2. Okay. So now let's take a look at the details of some of the measurements. Okay. So slides are clear. Yeah, now it's clear, right? Okay. If you look at it, it has a 5 configurable gear, namely called the gear 1 to gear 5. You can kind of configure the A-PHY into different gears, but we'll have to make sure that lower gears are supported. What does it mean is that if your interface supports a gear 3, you'll have to make sure the gear 2 and gear 1 being supported. In order to have a better throughput for the given cable, so the 2 different types of signaling has been used. So it has a better data rate. If you look at the gear 3 with 8 gigabits per second, that net app data rate goes up to 7.2 gigabits per second. If you look at the gear 5 at 16 gigabits per second, the net app data rate goes up to 14.4 gigabits per second. In order to ensure that interoperability, there were many tests have been defined. So, but if you look at the compliance test specification document, which will be made available to MIPI member, so it's broadly divided into number of groups and many sections. So Some of the sections are something like to cover the test requirement, like file layer, electrical specifications, and operation modes, data link layer, control and management. So out of these sections today, I shall be focusing on electrical specification for the transmitter and the receiver here for both downlink as well as the uplink. Some of the measurements are common for both downlink and uplink. So if you look at it, some of the TX measurements which is on the table on the left-hand side here, the TX power spectral density, droop, jitter, symbol rate accuracy, downlink eye opening, and linearity is applicable for PAM type of signaling. The right-hand side is about the receiver requirement. So some downlink RX bit error rate measurement and then RX symbol rate frequency tolerant. So most of the TX measurements are performed by operating the DUT in test mode so that it will generate the required signal and transmit it. So those signals will be acquired and the measurements being carried out, and to ensure the compliance of the signal integrity. The RX measurements are being carried out by measuring the BER, but with noise being present on the signal. So it's not only applying data as it goes through the cable, we also add the noise and then perform the bit error rate measurement. Now let's get into the details of the TX measurements. So before getting into the detail, let's take a look at the setup for the TX measurement. The TX testing involves performing the compliance measurement at all gears for the source DUT. That means if a device is operated gear 3, you'll have to perform the compliance TX measurement for gear 1, gear 2, and gear 3. Okay. So there are 2 steps involved to complete the measurements. The first step is to make the source DUT and then put it onto the test mode. This can be done by 2 different steps. One way is to perform, if the DUT supports an external controller, you can program the source DUT and then put it on the test mode. The other way of putting the source DUT in the test mode is by making use of the link partner. The link partner can force the source DUT to the test mode and then leave it there. Then after that, we can disconnect the link partner and then divert the signal back to the measuring equipment. So the test mode 1 to test mode 4 are used as a test mode here. We set these modes based on the measurement requirement, but we use the test mode 1 for power spectral density, test mode 2 for the droop, test mode 3 for the jitter, test mode 4 for the eye opening. And for today's compliance measurement, I will be focusing on power spectral density and for the NRZ signal and PAM signal, and I will also be focusing on the linearity measurement. So these 2 measurements are more complex compared to other measurements. So now let's take a look at the power spectral density measurement. The power spectral density is a very important measurement because we need to ensure when the link is under operation, the frequency component of the link should not interfere with any other type of the communications. So the objective of the PSD is to measure the power spectral density of the current link is well within the limits and well within the limit so that it doesn't interfere with any other links in the operating environment. So the performing the PSD measurement need that we need to acquire the signal and we need to capture the signal entire test mode block, the test mode 1. The test mode 1 has been designed in such a way that it has got all the frequency component, which is a 512 microsecond block of the consecutive symbols. So we have to acquire this signal with 8 times the oversampling. There are 2 ways to acquire the signal. One is called acquiring the long record length and then segment that TM1 repetition and then perform the measurements. The other way of doing it is that doing the 8 repetitive acquisition, identifying the test mode signal 1 start and stop, and then perform the PSD measurement. Since we need that resolution, a PSD measurement need to be performed at 120 kilohertz resolution bandwidth, we acquire the 8 times the waveform and then perform this measurement. So after we acquire the waveform, we pass on through that algorithm, which is developed with MATLAB and has got a built-in max hold function. So all the 8 waveforms have been passed, and then power spectral density has been measured. Once we measure the power spectral density, each frequency component being compared with the kind of the limit values. You can take a look at it. The PAM-based power spectral density at the top and energy-based power spectral density at the bottom. So the limit values for the power spectral density are different for PAM and NRZ. Now, let's take a look at the other measurement called the PAM linearity. So linearity measurements, generally the linearity measurement is applicable for the PAM-based signal. Generally, we measure the linearity by looking at the eye opening at the middle eye and the top eye and the bottom eye. But here we are going to measure as a distortion ratio, that is signal to noise ratio. So generally what we do is that we measure the linearity for PAM4 signal by acquiring the waveform, and we also have the waveform that is simulation for the same signal. We call the simulated waveform as a reference. Then we acquire the signal from the DUT. Then what we do is that we identify the start and stop of the repetitive pattern. Then we overlap it, then average it, and then remove the noise. Then second is that we normalize that averaged pattern. After now averaging the normalized pattern, then we'll compare it with the reference pattern and compute the linear canceller using the reference pattern using LSM method. So once we calculate, then we calculate the distortion. When compute the distortion for 10 consecutive phases, that means I need to sample that signal with 10 samples per UI. I need to have about 10 samples per UI. Then I'll have to make sure the 4 consecutive samples are kind of meeting the and should be less than the limit values. If you look at the right-hand side bottom, that distortion for RMS phase, it should be less than minus 30 dB. The 4 consecutive phases are less than minus 30 dB. Look at the bottom of it, the distortion peak RMS value should be about minus 18. So it's kind of minus 20, minus 25.94. So the 4 consecutive phases are less than minus 18 dB. So this is the way it's measured. The more complex is that the complexity of this measurement is that identify the start and stop of the test mode signal, overlapping it exactly, and then averaging it, and then calculate the distortion. Okay. So this completes some of the sample measurements of the TX. Now we'll get into the next interesting stuff is a receiver testing. Basically, how the receiver testing being done, let's take a look at the setup. Because previously Raj talked about in a simulation environment how the receiver is being done. So generally, we perform the receiver test using a bit error rate measurements. The bit error rate in digital communication system is defined as the estimated probability that any bit being transmitted through the system will be received in error. BER is measured by transmitting a finite number of bits through the system and counting the number of errors received. The ratio of number of bits received as an error with the number of bits being transmitted is called BER. The most bit error occurs due to the random or system noise. The BER is measured and it should be less than 1 e⁻². The setup consists of the link partner, which acts as a source. So that you can see over here, link partner SRC-Testir. And sync DUT is connected through the test fixture and also the golden cable called GCT1-3. So the golden cable as a characteristic correspond to the worst case cable defined in the specifications and goes up to 28 dB attenuation at 4 GHz for shielded twisted pair cable. The link partner signal is passed through the golden cable, then through the test fixture coupler. The coupler is responsible for coupling the external noise signal from the AWG noise source and also maintaining a bidirectional communications between the link partner and the sync DUT. The test coupling fixture will have a direction coupler, and the AWG signal is being amplified before being coupled to the signal that is coming from the link partner for the testing. For all the BER testing, configure the sync DUT in test mode 6. So in test mode 6, when the DUT has been operated on the test mode 6, the link partner will establish communication with DUT through golden channel and fixture as using a unidirectional startup procedure. Once the communication is established, set the DUT for the BIST operation where it detects the BER error. Now, so once this has been tested, then switch on the AWG, add this noise to the link partner signal, and then perform your BER test. So the BER value can be read from the sync DUT registers. Okay. Now let's take a look at the type of noise that we need to inject for receiver testing. So if you look at one of the noise, important noise is ingress noise. The RF ingress noise is a radiated EMC model based on the multiple modulation scheme and testing its effect on 15-meter cable at any instances. There are two types of profile. One is the profile 1 and profile 2. We know profile 1 is NRZ based signaling and profile 2 is your PAM based signaling. On profile 1, we'll test up to 5 millivolt peak up to 6 gigahertz, and other profile 2 with 40 millivolt up to 6 gigahertz. It is based on ISO standard. Generating this noise is challenge because it needs to be generated as a signal with multiple modulation and spread across the frequency range up to 6 gigahertz. We also need to control the amplitude of the signal such that it meets the requirement of 40 millivolt peak up to 80 millivolt peak to peak. So before we couple the signal, so we need to measure it. So we generate the signal, couple it using the direction coupler, then measure the ingress signal at the input of the receiver. So the measured signal should have about 80 millivolt peak to peak. After adjusting the level of the signal, coupled with the BER signal from the link partner. After coupling this noise, enable the BER BAST measurements on the DUT and measure the error. So this is about the one of the noise, the ingress noise. The next noise is a very interesting one called the fast transient noise. The fast transient noise is to ensure it ensures the fast and slow pulses. It is based on ISO standard. It has a pulse frequency of up to 40 megahertz using a crosstalk from power cable transient into the data lane. It has a decaying sawtooth model at 40 megahertz with 4 nanosecond rise time and the signal falls from 150 millivolt all the way to 15 millivolt with 150 nanoseconds. Before we couple the signal, we need to measure it or calibrate it. So we generate the signal and couple it using the direction coupler. Then measure the fast transient signal at the input of the receiver. The method signal should have the 150 millivolt peak. So as you can see over here. After adjusting the levels of the signal, then couple it with the kind of data from the link partner for the BER testing. So after coupling this noise, enable the BIST on the DUT and then perform your BER test. This signal is repeated at a rate of 10 megahertz. Next, the third important noise is the crosstalk noise. As we know, in case of an automotive environment, so there will be a cluster of cable. The cable have been joined together. Okay, the crosstalk noise, so is important noise. This test is to ensure the A-PHY shall tolerate alien crosstalk bundle related to the crosstalk broadband noise inserted at the input of the receiver. Before we generate the signal, we need to make sure the signal is well below the limit line. So the figure represents the characteristic of the noise and its PSD should be close to the limit line. You can observe the theoretical PSD, theoretical results of the PSD. I have the crosstalks is in blue color and the yellow color is that signal generated, then acquired, and then carried out the measurements. So if we look at it, the peak-to-peak amplitude is about 1.42 millivolts. It's difficult to kind of generate these kind of signals and to have this characteristic. So we use kind of 10 dB front-end attenuator of the AWG to generate this kind of a signal. And then the final setup of the RX looks like this. It's A-PHY. We have a link partner, so signal being fed through the golden channel, and we have a direction coupler. So the direction couples the signal from the noise source, and then once it's ready, then we'll give it to the DUT for the BER testing. So in summary, so The serial data testing in IVN is not unlike testing the consumer interface, because we have to ensure the data link is working at different environment to meet the higher safety and reliability needs. Interoperability testing need not only cover the file level, but also include the application layer. The serial data link is not only limited to compliance or interoperability requirement, the need is also to evaluate all sorts of functionality requirement and to ensure the link is working and all other systems are under operations. So thank you for your attention. Now we're ready for questions and answers.
Thanks, Ramesh. Sorry to rush you at the end there. Okay, we just got literally time for probably just one or two very quick questions. One that came in through the Q&A was just a question regarding when the conformance test suite for A-PHY will be available. I don't know if you can give an indication.
When the A-PHY testing, confirmed testing is might be available. So still the work is under progress, because I don't have a timeline at this moment. So the work is under progress.
Okay, so we'll come back offline. What is monitored for the RX BER measurement? Does PHY need to implement any hardware for BER monitor, which will be used by test equipment?
Okay, so for BER monitor, all we need to read that we'll have to put it on the test mode 6, and the BST operation ensure the error being counted. All we need to do is read the register for the DOT. It's a part of the implementation.
Okay, thank you, Ramesh. And I guess one just final question for myself. Obviously, you mentioned that TX testing, RX testing. Do you use the same equipment for both?
Okay, for TX testings, we need basically a scope. And for RX testing also, we need a scope as well as a noise generator. And we also need that the link partner.
We need to wrap it up there, I'm afraid. Sorry, a bit rushed at the end, but we need just to give a little bit of a gap between now and the next presentation. Thanks for your presentation today. Thank you for asking those couple of quick questions.